Now that we have really dived into what is an acid and what is a base and looked at predicting the products of acid dissociation reactions, we're going to start looking at characterizing acid strength and base strength with equilibrium constants. We'll be able to then use this to start to determine the pH for a solution, or like how dangerous it is, how many hydronium ions there are, uh, based on those Ka values and initial concentrations. And so we're going to kind of now get into more of the math piece of these acid and base problems. So let's dive in. So, acid strength, as we've already talked about, really depends on how many hydrogens are donated. So, what percentage of the acid is going to actually break that acid hydrogen bond, and that hydrogen will be donated to a base? If it's like really, really high, then we have a strong acid, right? So, that percentage that it ionizes or dissociates. Is going to tell us strength. And we're going to characterize that with equilibrium constants. And so we're going to have what we call the acid ionization constant, which we're going to call K with a subscript A. Uh, Ka is it's just an equilibrium constant. We put the subscript A so everyone knows we're talking about an acid dissociation reaction. But I mean, it's the same thing. It's going to be the concentration of the products with the exponents as or the coefficients as the exponents divided by the concentration of the reactants with the coefficients as the exponents. Now, usually with acid base reactions, though, it's kind of nice. The coefficients are usually just 1 to 1 to 1 to 1 because we're just having one hydrogen atom move from an acid to a base. So that can simplify this in some ways. In general, when we have really large K values, that means that we have, so these large Ka values mean we have a higher concentration of products than reactants. Or we'd say that products were favored. And so that means that we're going to have a lot of our acid molecules that have donated that hydrogen. And so that's going to always correspond to a stronger acid. So large Ka values correspond to strong acids. So just a reminder, so we're looking at this equation right here. Let's actually use a different color. Where we've got our acid plus water is going to form hydronium ion and the conjugate base of our acid. And this is using essentially a variable form of what an acid is. So A is just representing anything that has an acidic hydrogen. And so for an equation like this, we're always going to ignore anything that is heterogeneous, right? So the liquid. So anything with a different phase, we're going to ignore. You could also think of it as being 1. And so that's going to give us an equilibrium constant or acid dissociation constant equation that looks like this, where we have our hydronium ion times the conjugate base divided by the concentration of our acid at equilibrium. You might see it written like this too, where it's the H plus instead of the hydronium ion. These are equivalent. So here's like some kind of context setting, some different acids. So we see the Ka value right here. So this Ka value is going to, as it increases, correspond to a stronger acid. And so here we have chlorous acid, which has a 1.1 times 10 to the negative 2. So in this case, this is a value, right, that is going to be less than 1. So we know it's going to be a weak acid. Or we could say that the reactants are favored. But it's still a lot stronger than something like hydrocyanic acid, which has a much smaller equilibrium constant, right? So if this is much smaller, this K is much, much less than 1. So it barely forms any product. So this acid is very weak and weaker than our chlorous acid. So let's walk through just an example of how to calculate this looking at hydrocyanic acid again. So let's calculate the acid dissociation constant for this reaction. And what we're always going to be looking at when we do these is we're going to be looking at the dissociation reaction. So you may need to predict the products of that. You may just know the acid is added to water. So if I say, here's some equilibrium concentrations, but what's that dissociation constant for hydrocyanic acid? And I just give you the acid, then that means you need to be able to add the acid to water and predict the products, and then build your expression from the complete reaction. And so I have it written out here. And we have concentrations at equilibrium, which is helpful. So writing this out, remember our equilibrium constants are always going to be our products over our reactants. So a few things to note. I'm not including water because it has a phase of liquid rather than aqueous. Also, all of my coefficients here are 1. So all of my concentrations are going to just be to the power of 1, right? And so I'm just going to omit that because if I have 1 molar to the power of 1, it's still 1 molar, right? Or 2 molar to the power of 1 is still 2 molar. So it seems repetitive to write it. If it helps you remember that, you're more than welcome to. And so those would be in like this, but I'm just going to leave them off. Because it doesn't really change how I'm going to solve this. All right, and so now I'm going to be able to just go ahead and plug in values from my equilibrium concentrations. And so I'm going to do that. So my cyanide concentration is going to be 4.9 times 10 to the negative fifth. I'm multiplying that by the hydronium ion concentration, which is the same, 4.9 times 10 to the negative fifth. And I'm going to divide that by my 5 molar hydrocyanic acid. And I'm just going to plug that into my calculator. And when I do, I get a value that is 4.8 times 10 to the negative 10. And so what I learned from this, right, K is extremely small. Therefore, this is a very weak acid.